In engineering mechanics, one of the most fundamental concepts you must understand is the difference between scalar and vector quantities. These two types of physical quantities form the foundation of how we describe motion, forces, and almost every physical phenomenon in civil engineering and physics. A scalar quantity is a physical quantity that is completely described by magnitude only. It does not require any direction to define it. For example, when we say that the temperature is 30 degrees Celsius, or the mass of an object is 10 kilograms, or the time taken is 5 seconds, we are dealing with scalar quantities. These values tell us how much of something exists, but they do not tell us anything about direction. On the other hand, a vector quantity is a physical quantity that requires both magnitude and direction for its complete description. For instance, when we talk about force, velocity, acceleration, or displacement, we must specify not only how much, but also in which direction. If a force of 10 newtons is applied, that information is incomplete unless we also state whether it is acting to the right, left, upward, or downward. Therefore, vectors are essential in engineering because most real-world problems involve direction-dependent behavior. Understanding the difference between scalar and vector quantities is crucial. Scalars can be added, subtracted, multiplied, or divided using simple algebraic rules. However, vectors follow different rules because direction must be taken into account. For example, adding two scalar quantities like 5 and 3 simply gives 8. But adding two vectors depends on both their magnitudes and the angle between them. To properly work with vectors, we need a way to represent them. A vector is typically represented graphically by a directed line segment. The length of the line represents the magnitude of the vector, while the arrowhead indicates its direction. In mathematical form, vectors are often written in bold letters or with an arrow on top, such as A or vector A. In coordinate systems, a vector can be expressed in terms of its components along the x, y, and sometimes z axes. Vector addition is one of the most important operations in mechanics. When two vectors are added, we cannot simply add their magnitudes unless they are acting in the same direction. Instead, we use graphical or analytical methods. One common graphical method is the head-to-tail method, where the tail of the second vector is placed at the head of the first vector. The resultant vector is then drawn from the tail of the first vector to the head of the second vector. Another method is the parallelogram law, where both vectors are drawn from the same point, and the diagonal of the parallelogram formed represents the resultant vector. Vector subtraction can be understood as adding the negative of a vector. If we want to subtract vector b from vector a, we reverse the direction of vector b and then add it to vector a using the same rules of vector addition. This concept is particularly useful in determining relative motion and equilibrium conditions in engineering problems. To simplify calculations, especially in analytical methods, vectors are often broken down into components. This is where unit vectors become extremely important. A unit vector is a vector that has a magnitude of 1 and indicates direction only. In a two-dimensional coordinate system, we commonly use I and j as unit vectors along the x-axis and y-axis respectively. In 3 dimensions, k is used for the z-axis. Any vector can be expressed as a combination of these unit vectors. For example, a vector a can be written as a equals ax edo plus ayj, where ax and ay are the components of the vector along the x and y directions. This representation makes it much easier to perform vector addition and subtraction, as we can simply add or subtract corresponding components. Unit vectors not only simplify calculations, but also provide a standardized way of expressing direction in space. This is especially useful in civil engineering, when analyzing forces in structures, calculating moments, or solving equilibrium problems. In summary, scalar quantities deal only with magnitude, while vector quantities involve both magnitude and direction. Vectors are represented graphically by arrows and mathematically by components. Their addition and subtraction require special rules that consider direction, and unit vectors help us express and manipulate vectors efficiently in coordinate systems. Mastering these concepts is essential for solving real-world engineering problems accurately and effectively.